Magnetic fields and electromagnets. First, let's look at the field around a bar magnet. Here we have a bar magnet underneath an overhead transparency. We sprinkle some iron filings onto the transparency above the magnet. Tapping it slightly, we see the iron filings align up on the field. We could represent field lines like this. See the little compass needles change direction when the magnet comes nearby, and as I move it to the other side, we see the compass needle changes direction. The magnetic field line is defined by the direction that the compass points in. It comes out of the North Pole and goes back into the South Pole. If we add other lines, it'll look like that, and it's strongest where the field lines are closest and weaker over there. Magnetic field lines around a solenoid when current flows. Have a look at the compass needles. Just like the magnet, we now have an electromagnet. Current is flowing in the coils, the solenoid, and that's the north end of the electromagnet, and notice how it turns around and changes direction, and where it goes in to the coils is the South Pole. Let's change the current direction. Swapping the terminals, we see the compass needles swing in the opposite direction. So that's the North Pole, and where it goes in on the other side is the South Pole. Building an electromagnet. Now you're going to be supplied with this equipment. Take just under half of the wire, wind it around a few times, and then tape it so it doesn't unwind, and then continue winding it until you have 30 coils on the iron rod. Secure it with tape on the other side. Now we're going to connect the ends to a cell, and we notice how it picks up the nails. We count how many nails, and we record that. Now we're going to try increase the current strength. What do you think will happen? We use the paper roll just to hold them together, and this time we see it picks up many more nails. So the strength of the magnet depends on the current. Now we wind a second layer, another 30 coils. And we go back to one cell. What do you expect? And again, you count the number. Let's have a look at the field direction around the electromagnet. That's the North Pole. See the compass needles pointing away, and flipping it around we get the South Pole. Let's change the current direction by turning the torch cell around. And we notice how that is now the South Pole. The north has become the south. So the advantage of the electromagnet is that you can switch it on and off. You can vary its strength by changing the current or the number of windings, the number of coils, and you can swap its poles. An application is in an electric motor. Have a look at this magnet that's spinning on a watch glass. See how the opposites attract, and if you keep swapping the one around, it keeps the other one spinning. And that's basically how all motors work. One magnet spinning inside the field of another that is constantly changing its poles. And this is easy to achieve for an electromagnet.